See if W3 School has anything good on object-oriented Python. Yeah. So you can reference that W3 Schools as well. But okay, so let's get back to object-oriented programming. Once it stops dropping frames. Is this even recording at all at this point, or is it just dropping everything? Is my internet connection down? No. I don't know if it sure seems like it. Yeah, so it's supposed to be 10 frames per second. As long as it's doing the audio, I guess. I'll check in a minute. Okay, so let's take a step back. Object-oriented programming. So I'll give the 2-minute version of why we need it. So in the olden days of programming, when they first invented computers, we were solving problems. They were generally mathematical problems. Like I wanted to run a bunch of simulations, which usually were just a bunch of equations, or maybe an algorithm, like a sorting algorithm. I wanted to alphabetize a bunch of files or something like that. And there was a lot of batch-style programming where we would have an input, a very distinct input. We'd run it, and we'd get an output, and that'd be the end of the program. Over time, software started to get larger, and we had to start managing this because we went from programs that were maybe thousands of lines of code to tens of thousands or hundreds of thousands or millions. And once you get that big, it's difficult to manage. If you remember last time, the analogy I gave is that if you're just going to build a shed in your backyard, the level of planning is probably relatively small. You might just sketch it out on a piece of paper, and that's the end of it. But if I'm trying to build a very large building, well, that gets much more, building a building is much more than just putting a bunch of concrete blocks on each other. It's not just like, oh, I can build the first floor, so I just build the second floor the same, the third floor. There's got to be some effort and organization into that process. Software is kind of the same thing in that I can build a very small program without a whole lot of planning. But as we start to get into larger programs, we have to start to break things apart into modules and say, how are these modules going to interact, and who's an expert at this module as far as like if it's database work or maybe engineering level stuff, that type of stuff. And so early programming languages didn't really offer a whole lot in the way of code reuse and breaking things up into functions. A lot of these are actually more relatively modern things. And what people started to realize is this is kind of the beginning of a field called software engineering, that a program is much more than just a collection of a bunch of if statements and loops. And so with this field of software engineering, they said, okay, well, realistically, statistically, people are going to have a bunch of tasks that are common. Now, for these very common tasks, what I might want to do is just create a reusable library. Or I might want to get into these things called design patterns, where, if I want to store a value once globally for the program, they came up with this pattern called the singleton pattern, things like that. And they kind of brought us this field of software engineering. And then also languages started to evolve, and people started to say, okay, rather than just it being a set of instructions, I'm going to create a programming language that just has a different view. Like a program is essentially an algorithm, or a program is essentially a bunch of functions, or the procedural view of the world, or Lisp's view of the world, like everything's a list. Now, one of those was object-oriented programming, which was essentially that all programs are just a collection of classes and objects. And what I mean by that is that just like the world is a collection of people and desks and printers and sand and clouds, same thing with a program, is that you could really compose a program if you broke up that program into a bunch of objects. And the basic idea was that, okay, well, if that's my view of the world, and that's how I'm inventing a programming language, what makes up an object? And essentially what makes up an object is two things. Does anybody remember those two things? Starts with an S and a B. So the object's current state and its behavior. Now, state is typically represented as what? Variables, exactly. And behavior usually means functions. And the idea is that those functions, exactly. And so when we're dealing with object-oriented programming, they're not plain old functions anymore. They're what's called a method. Now, there's like a 90% overlap between what a function is and a method is. They're very similar. The difference being that, like, the idea of a method, it's basically a function where I can access all those. Remember I talked about the state? That method is actually able to access the current state of the object. Okay, so we talked about that an object is essentially, we're going to have its state and its behavior. So let's go ahead and it's very common when you're first learning object-oriented programming to deal with real-world objects. But as I mentioned last class, that's not always the case. I might have a class called like DB, DB just for data, or I might have one for network connections. Or if it's a video game, it actually could be something like that. Like it could represent a character on the screen, and their state is like where they are on the map, their current health, which direction they're facing, any controls that are currently being applied, and then the behavior would be like changing those. Like, so if I'm a player and I apply the controller, if I press a button that makes the character do something, that would be changing the behavior. But more frequently than not, that it tends to be very abstract things that there's maybe not necessarily a real world equivalent, like a database object. Okay, so let's start with some real world things just to make our lives a little bit easier. So let's make a class called dog. And remember, so that's the general view of the world, is that we have objects and they have state and behavior. Now once we get into kind of the specifics, I have to define what a dog actually is. That's going to be my class. That's going to be my blueprint from which I actually make specific dogs. So imagine if you're, again, like the example I like to give, maybe if you're working in a factory and you're trying to manufacture, doesn't really matter what, let's say shoes. There might be a set of directions. Let's say, okay, this is how you actually make the shoes. You take this material and sew it and add in laces and so forth. And at the other side, you get an actual specific shoe. So this is kind of our blueprint for how to make a dog and the properties of a dog and the potential behaviors of a dog. But then we make a concrete instance of a dog where that would actually be somebody's specific pet. Okay. So now, let's do this. So we'll say def, and then we'll create a method called bark. And then what did I already forget? So remember, yeah, exactly. So remember when we're doing these methods, we have to put this keyword self. Now, if you remember, so right now this is going to be the behavior. This is a method. If you remember, we had this thing called a constructor. And the idea is that when you make a concrete instance of that dog, the constructor runs. And it's very convenient because at the time that dog leaves the factory, I guess that's a bad example. There's not really a dog factory. Maybe a robot dog. As soon as it's created, we want to know that a certain set of things are true. Okay? So that's what the constructor does, is that as soon as we create a dog, we can execute some code before anything else happens. And let's say, for example, we want to specify that dog's weight in whatever units. Let's say pounds, 20-pound dog. Let's just go ahead and print the dog's weight. So when we create this dog, we're saying, okay, this dog has a weight of 20 pounds. But the way we've written this is going to create all dogs as having a weight of 20 pounds. So this might not be too useful as written because it's kind of making an assumption that's maybe not true. So what we can do is we can pass this in, and when we call the constructor, we can actually pass in the value for weight. So for now, let's just call this W. Because we're going to say self.weight is equal to W. And now when we create a new instance of the dog, we can pass in the weight. So maybe this dog is going to be 22 pounds. So I cheated a little bit, and I've done this before with functions because I didn't want to get into scoping, but I think we do have to talk about this. So this is a method, but it's still very similar to a function. If I create a variable, weight, I can make a variable weight local to that function. Or let's use another example. Let's say just x. If I just put some variable in there, x. So don't type this, but let's do this. Let's say, so again, don't type this because I'm going to change it. If I say x equals 5, and then print x over here, I was going to say, does this work? But obviously it doesn't. What I've done here is I've created a variable that's local to this particular method. It's not local to dog. It doesn't belong to dog. It just belongs to this function right here. That's why this doesn't work. But if I were to do print x here, this does work. Do you see the difference? X is local to this function right here, and that's why this works, but it's not accessible anywhere else. But if I make it a part of the dog, then it is accessible to every single function. How do I do that? I say, okay, self.x and now this is a part of every single function. You see the difference? So that self keyword essentially is basically gets you the current reference, the current context of the dog, essentially. So it's not uncommon to do this instead. is to say okay, the variable that I'm passing in is weight, and the dog version of weight is equal to my local version. Does that make sense, the difference? If this doesn't make sense, we can just go back to the simplified version of just using W. For now, let's just use W. I don't want to confuse anybody. You will see this sometimes. That's why I wanted to bring it up. But for now, let's cheat a little bit before we can really get a handle on contexts and how and scoping and how that works. Okay, so we've got this dog that can bark. The dog's got a weight. Remember, we talked about this last time, that we don't necessarily want somebody just to be able to go in and just set the dog to any weight. Like, for example, we wouldn't necessarily want it to set to a negative weight. So what we can do is we can wrap a function around it and have set weight, pass in self and W. And then now, I can put in a check if I wanted to. I can say, well, it'd be kind of silly if they put it in a negative weight for the dog, so let me just make sure that W is positive. And right now, we're just going to silently fail, which isn't great, but I don't want to throw too much at you just yet with exceptions. What's that? It just won't. So if you pass in a negative weight, it's just going to silently not change it, which is generally bad. If like I tell you to set the weight and nothing happens, that's generally bad.
You want an exception.
Exactly. You put in else, throw exception, value error, and then pass in the string, cannot set a negative weight. Yeah. Okay, and so now we can do that if we wanted to set the dog's weight to a new weight. What I'd do is idog dot set weight, and now let's say the dog is a little bit heavier now. It's 23 pounds. So that's essentially what we did last class. Okay, is there any questions on this? Everyone make sure you understand the terminology. That's exactly where I'm leading to. So we've got methods. Methods are essentially functions that are part of that class. And what that means is that I can actually, for that particular dog, within a method, I can access its weight, I can set its weight, I can do whatever. A regular function can't do that. A regular function can't just magically, access the dog. We'd have to pass in the dog as a parameter or something like that. And then we have instance variables, like for example, weight, where that particular dog's weight. And we have the constructor, which runs right here. Line 13 will actually create a new instance of that particular dog. Remember, we talked about the idea of a blueprint of a dog, all the characteristics, like if you're reading about a dog in a book, what a dog is, versus your particular pet, your particular dog that you own. So let's take this example a little bit further. Let's have a cat. Now, I'm going to be a little bit lazy and copy and paste code just to save a little bit of time. And a cat doesn't bark. What does a cat do? Just meow. So let's change it to that. So when you're taking a view, a view of the world that everything's an object, things aren't really just independent objects. So what I mean is, like, if anybody's ever taken a biology class, we have these various taxonomies where we say, okay, well, it's a part of canine, whatever that is, I don't remember, kingdom, phylum, all that. But let's say, for example, like golden retriever is a canine. You know what I mean? Like, we have these what are called taxonomies, these organizational structures. Because you could have a German Shepherd and a Chihuahua. They're very different dogs, but they're both dogs still. Same thing with a dog and a cat. They're different in many ways, but they're still animals. And more specifically, they're both mammals. What I've done here is kind of bad because they're both going to have a weight. And essentially what I've done is I've copied and pasted code. I've got duplicate code. And so what we do to handle that is we have something called inheritance. And the things that a dog and cat have that are the same, we can inherit. So a dog and a cat are both going to have a weight. So why have copied and pasted code when we can factor that out into some common place? Now going back, what's generally bad about having duplicate code? Why is this? It's not gonna break in itself, but it's potentially problematic long term. Exactly. If we change one thing, we have to change it in multiple spots. And the realities of software development are that it might be somebody else changing that code 10 years later. It's just not a very efficient process because you have to find all the spots that you have to change. So there's just many problems with it. In itself, the code's still going to run fine. But again, code is changing. It's very rarely that you write a program once and that's the end of the program. It's kind of this evolving thing. So let's go ahead and do that. Above dog and cat, let's go ahead and make a class called animal. And let's go ahead and it didn't paste very well. That's one of the tough things with Python is copying and pasting. What's it complaining about? Oh, it's lining everything up. So this should be right here. This should be here. And I think we're good now. So now any animal can have a weight, and we can change that animal's weight as needed. Now right now, this isn't anything. I've got 3 separate classes. So what I have to do is inside of the dog class, I have to specify, hey, the parent of this dog is going to be animal. So the way I do that is right here in my class definition, I just write what it's inheriting from. And here I'm going to say it's inheriting from animal. And now I can actually get rid of this duplicate code. So now that all the dog is responsible for is barking.
Like Java, can you make empty methods?
You mean like abstract, like to where?
Abstract.
Yeah. You tend not to. It's weird. Python isn't like a super strictly object-oriented language, so it's missing a lot of things. Like, and so what people, yeah, and so there's not really a keyword modifier to set something as abstract. It's just kind of like up to you to do it. Does that make sense? So it's not enforced, I guess is the correct word.
I mean, if I was a Java programmer, which is why I'm not, I probably would call it just empty instead of abstract.
Yeah. One of the interesting things with Python is that you don't actually see people do a whole lot of object-oriented programming in Python. What a lot of times people do is they make modules with functions. They still do it. A lot of people do it, but it's not like Java where everything is object-oriented. It's like with Python, it's maybe more like 50-50.
I noticed sort of kind of in the contrary is that the big Python projects, their objects are separated into files.
Exactly, and the modules, yeah.
In the modules, yeah.
Well, yeah, that's essentially files, yeah.
And at the bottom is like, for debugging purposes, at the bottom of every single file, there's a main function.
Yeah, that's actually super useful. For those that don't know, actually Python is one of the few languages that have built-in testing, which is really cool. I don't know if we'll have time to go over it, but the actual language itself has, in Python 3, it has built-in testing, which is really cool. Okay, so we can do the same thing with cat, because cat is going to have a weight, and all the cat class is responsible for now is to meow. So let's really think about this for a second. I've got this class, oh, and then we actually want to say that cat inherits from animal. So let's take a step back. Let's make sure we know exactly where we are in this whole thing. So we've taken the commonalities between dog and cat, and we've pushed it up into a parent class called animal. And really right now all that parent class does is the weight. And what I'm telling you is that by default, we automatically get that behavior, because notice that I don't need to actually change any of this code, because I'm creating a new dog and I'm calling the setWeight method. Well, dog no longer has a setWeight method, so where is it calling the setWeight method? It's not calling it on dog, it's calling it on which class? Animal. And so let's test that to make sure that works. We run it, and that's really interesting because I can set the dog's weight, I can get the dog's weight, but the dog never actually specifies the weight. It automatically inherits all this stuff from animal. If I decided that I don't want to actually inherit animal anymore, this code isn't going to work. This is completely dependent on, well, anyway. This is completely dependent on it inheriting from animal. But we can even factor out some even more things here if we really think about it. We can say, okay, well, a dog is going to bark and a cat is going to meow, but really what they're doing is they're just speaking or making some sort of noise. They just make a different noise. So if we're clever about this function, what we can do instead is have one generic method called speak, and then have it return that thing. So Python actually has, this is actually what we were just talking about. In other languages, what you do is you define speak in the parent. But an animal doesn't really speak. You know what I mean? Like if I told you what noise does an animal make, the first question you're going to say, okay, what type of animal? Is it a dog, a cat, a bird, whatever? So this doesn't really make a whole lot of sense. Instead, in Python, what we do is we have something called duck typing. And this is a very strange subject. In many ways, Python's an easier language to learn, but it's a more difficult language for people to get their head around, because like something like Java is really, 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 really structured. And I can give you all the rules for Java, and they're very internally consistent and structured. Python is more of a practical language. And so what they came up with this idea is it's called duck typing. And it's from that old saying that if it looks like a, what is it? If it walks like a duck and quacks like a duck, then it's probably a duck. So what we can do here is instead of having bark, we can change both of these to speak. And because both of them have implemented speak, it's going to work out without any problems. Python's a little bit looser and more open-ended. It's the, in other languages, what you do is you have to specify up front, like in a contract, in code, and say this is exactly how it's going to act. Python, it's more like up to the programmer just to be consistent and kind of be mindful of that, okay? What's that?
It's up to the programmer whether or not they want to be consistent.
Yeah. There's some pros and cons to it. Python is great for scripting. For doing large-scale software engineering, I don't know if I'd do that. I might kind of revert back to one of the more traditional languages like a C++ or a Java, or even Google has a language now called Go. There's another language called Rust. It's really, really great for scripting. I use it for a lot of things related to scripting and a lot of other things. But if you wouldn't really write a web browser in Python, you wouldn't write like a phone. Like if you're AT&T, you probably wouldn't write, have a whole phone system in Python. But it is really good for scripting purposes. Like if I'm doing data science and I have a bunch of data I want to clean up and a bunch of messy tasks, it's really, really, really good at that stuff. So you just kind of know when to use it. That's why I say is that like you don't tend to see as much object-oriented code in Python as you do in say like Java. It's because in practice, once you get to this level where you're doing a lot of object-oriented programming, sometimes you might have to take a step back and say, is this project really a good fit for Python? Okay. Now that being said, if I were to guess, I'd say most projects are small enough that they could still fit in the Python world, and that it's, unless you're working for a giant company, the chances that you're actually going to work on a project that needs C++ is pretty low. Okay, so everyone understands this example so far? Let's take it a step further, okay? So let's open up a new REPL. And I like to have, let's do a grocery store here, okay? So in this example, I'm describing essentially data. But the animals aren't really doing anything. They're not really interacting with the world. Let's do this. Let's create a grocery store. And I'll just call it store. I don't think this example will need any inheritance, so you can kind of get that out of your head for a minute. I might do another example that does inheritance, but I'll probably save that for Monday. And it'll probably be the grocery store, and it'll probably be just to show you that you can write this a few different ways. Okay. So we've got self. Now, let's think, what might a grocery store have? Well, a grocery store probably has a bunch of food items. So we could do that. We could say, okay, self.items. I might say, okay, well, all these items could be represented as a list or as a dictionary. And that's true. But you have to think, if I want to look something up, if I want to look up a specific item, if somebody goes to the store and they say, I want to buy an apple, do you think it's easier to find an apple through a dictionary or a list? So let's think about what happens. If I try to find an apple inside of a list, what do I have to do? I have to go through the entire list. If I make a dictionary where the key is each food name, how difficult is it to find an apple? It's instant, right? Because I just look up, give me the data structure for an apple. So let's go ahead and we'll put this as a dictionary. And then in a store, I'll probably at the very least I will want to buy things. So let's keep life simple. Let's just have these two things so far. And let's just put pass for right now. And we'll create a new instance of the store just to make sure it works. And that's great so far. So if I create an instance of the store, I've got to give it some sort of inventory. Right now our store is inventory. Maybe that was a better word, but bless you. Inventory might have been better. Let's change it to that, I guess, inventory. Exactly, that's exactly where I'm going. So right now we have our store, and imagine it's like this Publix that's freshly built. And we build this Publix and it's got no items in it. So one of the things we might actually want to do is that when we have this, when we're building our Publix, we might actually want to be able to pass some sort of inventory. So let's go ahead and do that. We'll have inv. And then rather than setting it to empty, we'll say that inventory is inv, short for inventory. But now when we make a new store, I have to actually pass in some sort of inventory. So let's go ahead and do that. So we'll just do D for dictionary, because it's going to be a dictionary. Let's do this. We'll use the full word inventory. I just don't want anybody getting confused over scoping issues. I know that's always a constant problem when you're first learning a language. So we'll say that inventory is apple. This version, we're not going to have any inheritance. The version we do Monday will have inheritance. It's what I like to do a lot of times is like take the same problem and solve it multiple ways. This one's going to be purely dictionary based, where it's not going to have any inheritance at all. No, this is going to be a pure dictionary implementation, which is not that uncommon. Now, if I've got a store, it's doubtful I just have one apple. So what things might I care about with an apple? Let's keep it basic. I could probably care about a million things about an apple, but let's keep it basic. I probably want to know how many apples I have, correct? And what other basic thing might I need? If I'm a store and I want to sell this and I want to get money for it, what do I need? The price. So that sort of says, I can't just say apple is 5. That doesn't hold enough. So what does apple have to point to? Another dictionary. So say that price is $1.05, and the quantity, let's say we start off with 10 apples. And let's just do one more item. see, we've got soda. Probably not the healthiest choice, but whatever. $1.30. And let's do a low amount because I might want to do something. If we have time, I want to do something to where we run out. So I want to be able to like buy 3 sodas and then run out and then have it give us a message. Exactly, yeah. So if I try to run it right now, it's going to complain. It's going to say, I'm expecting some sort of inventory. So now we have to take this inventory that we just created and pass it to the store. Now, again, some of this is software engineering because imagine if I had hard-coded this inventory up here. It means that every single store I ever build is always going to have this inventory initially, which may not be true. By being able to separately define the inventory and say, okay, well, you know, this is in an area where they don't really buy a lot of soda. Maybe I want to have something else instead. I can actually pass in the inventory, or maybe 3 isn't very much for soda. Maybe I want to stock 20 bottles of soda. By passing in inventory separately versus hard coding it inside of the class, I can take that blueprint of a store and have various parameters. Just like somebody who's building bikes, it might essentially be the same bike, but maybe they just, you know, have little tweaks, like it's painted a different color or it has a slightly different tire size or something like that. But otherwise, it's essentially the same bike. So now, this is good so far. So let's make sure it actually runs this time. Perfect. If I want to buy an item, right now this is just kind of a skeleton. There's not really anything here. If I'm going to buy something, and I kind of already gave you the answer, what do I have to pass to this function to know what to buy? I have to actually have some sort of variable called like item or key or whatever. We'll just call it item. Exactly. And ideally, if they pass in something you can't buy, you'd throw a value not found error exception or something like that, yeah. But we'll try to keep this example simple for now. I'm trying not to introduce too much at once. So we'll say, okay, well, I'm going to go to self.inventory. I'm going to look up that item. And let's just say for simplicity right now, they buy 1 item at a time. So if they want to buy 3 apples, they would have to do buy, which is not realistic, but let's just say for now, we buy 1 item at a time. It's going to make a couple things easier in a bit. So let's go ahead and do that. Let's purchase. So we'll do s.buy, and we're going to look up apple. And then now if I print the inventory, it should have 9 apples instead of 10. So I was close. I missed one thing. I'm not subtracting 1 from the inventory. What am I subtracting 1 from? The quantity. Yeah, so I have to put 1 more pair of square brackets here. So it's going to look up the item, but the item contains a dictionary. So then from there, I have to get the quantity and subtract that by 1. Does that make sense to everyone? So all that's happening here is I've looked up something, and essentially what that something is, if I look up apple, it's going to return this. And then from there, I take that and then I say, okay, give me the quantity. And then now this version should work. And we can see here the quantity from 10 to 9. Now there's a little bit of a, I don't like doing this right here, print inventory. This isn't, in my opinion, that great of a thing to do. We actually have a bunch of special built-in functions. We've already seen one. They're called dunders. It's double underscore. And when you see that double underscore, it's kind of it's kind of telling you that it's something special. And there's a bunch of these that are built into the language. One of them is REPR, short for representation. And it's basically saying if I want to print a store, what do I want to print? Hold on, let me make sure I coded this correctly. Let me see if I can cast this to a string first. This isn't the best way to do it. There's better ways to handle this, but this is just cheating. Okay, so this will work for now. If I want to get a representation of that store, to me, the best way to get a representation of the store is to actually just print its inventory. So this is a special function that a method essentially that I've defined here. That if I want to print a representation of the store, as I've done here, I did print s. Well, s is the store. It's just going to give me back a string version of the inventory. Don't worry about that for now. This was just kind of an awkward thing to do print inventory because that's not really what we want. Okay, so you don't understand that now. That's all right. Just know that this little line of code here, if I want to print the store, this is going to let us print the inventory.
So did the store just modify the inventory variable?
That's why I didn't want to talk about it too much. So what happened is that this was passed by reference, so it actually modified the original. So if we wanted a copy, we'd have to do a deep copy. So we have to keep that in mind.
Because I would normally assume, that it would copy the variable.
Correct. Yeah, the only thing that it gives you a copy of is going to be primitives, like numbers and. So we have to keep that in mind. That's why I was a little bit apprehensive about doing that print like that, because it's not really great. This is not perfect, but this is a little bit better.
Different variables can interact differently with.
Yeah, I have a C background. I don't like it either. Like if I'm going to give you a reference or a pointer or something like that, I want to specify that I'm giving you a pointer or a reference. I'd rather have a full copy of the data, but Java does the same thing. Java is passed by reference unless you pass it a primitive. But anyway, okay. So one of the things that we want to check for is if I'm out of that item, I don't actually end up in negative territory. So let's go ahead and put a little bit of a check in here. So we'll say if, we can copy and paste here. If we currently have 0 of that item, we don't want to be able to sell it to them. So what we want to do instead is to check to see if they have more than 0, then it's okay to sell to them. I don't want to make this overly complex, but I want to kind of start to slowly introduce real-world things. Remember I told you before this isn't great because if I try to buy soda 4 times or 5 times or 6 times, I'm not actually selling, after the 3rd time, after I run out of soda, nothing's happening. I'm not actually selling it to you anymore, but it's just silent. It's not giving me any indication. So what we want to do is raise some sort of exception. Now, it's generally not a good idea to make up your own exceptions. You can, but what I usually like to do is just look at the built-in common exceptions that the language already gives you and find the closest thing. To me, this would seem like a value issue, like we've run out, but let's see if we can find something better. So key error, that would be a good example when we can't find, if I try to look up, like say, grapes, and I don't actually sell grapes. To me, I'm pretty sure value error is probably going to be the closest thing. Okay, so value errors when an operation received an argument that was the right type, but an inappropriate value, maybe not. Maybe there's something with overflow. That's not really great either. For now, let's just go ahead and we'll say value error for now, okay? And so to do that, what we do is we do raise. So we'll say else raise value error, and then we can pass it a string out of that item. So remember what exceptions do. Exception is basically like we have normal behavior, and our normal behavior is going to be when we have, you know, that item still in stock. But if we run out of that item, I've got to let you know somehow. In older languages like C, what you'd often do is you'd return a number, and that number mapped back to some sort of error. Most modern languages have built in what's called exception handling. And if you want to handle errors and exceptions and other non-normal flow of things, it's actually a separate built-in system. Because what happens is it kind of takes you off to the side and says, an exception happened, you can handle it and clean it up if you want to, and then keep on going with the program. Like in this program, this isn't a fatal error. This isn't worth stopping the whole program for. If somebody tries to buy some soda and we're out of soda, it's not like the whole store is just going to like freeze up, you know, and not work anymore. It's just you just tell them we're out of that item. Versus something catastrophic like, you know, if you run out of memory on the computer, that's pretty catastrophic. It's like we really can't move forward with that. That one's pretty difficult to recover from. Okay. So let's do this. Let's exactly, yeah. So let's just buy a bunch of bottles of soda. So it'll sell us this first bottle, and the second bottle, and the third bottle. But as soon as we try to buy that fourth bottle, so that's not a great message to the user. So what we can actually do is we can intercept that. And to intercept that, we use what's called the TryCatch block. Let's do this. Anytime you see code like this is kind of like a red herring that you're probably doing something wrong. So if I want to buy 4 bottles of soda, let me do this instead. For I in range 4, let's put this inside of a loop. And on the 4th time, it's gonna cause that, okay? So what we can do here is say, okay, try to buy a bottle of soda. If you can't, and you get a value error, I think this is the syntax. Hold on. Let me run this just to make sure this is the syntax. Yeah, okay, perfect. So what this does is it tries to perform the operation. The first 3 times this is going to work fine. But that 4th time when we try to buy it, it's going to throw an exception. Well, because we've put in our own exception handling, we can say, okay, well, that's not that big of a deal. Let's just tell them we're out of the item. And so we catch the value error. This gives us a reference to that. So we're saying value error as E just for error. And then we said, hey, something happened where we can't buy the soda. And remember that this little string right here that we passed, we said out of that item. We can actually let the user see that item directly. Now this is a little bit nicer of an error message that says, hey, can't buy that last bottle of soda. We're out of the item. This is, now we're really starting to get closer to a real world problem. This is a very, still a relatively basic program, but now we're starting to use real world stuff. Notice that we're kind of increasing in our complexity of dictionaries. This might be a real world dictionary. If you had some sort of very basic inventory that you were trying to keep track of, you could really realistically do that. You know, if you're just running like a very small store, you just wanted to know your price and your quantity for your inventory, and that's it. Maybe you could get more sophisticated and start to add additional things, but to me, this would be like the bare minimum that you could do that. And then if you've got some sort of, maybe you hook this up to a web interface, and then they tried to buy an item that wasn't there, you could, hey, throw an exception, let that exception bubble up to the web interface. So here we're actually starting to get into much, much more real world scenarios rather than COP2030 is always a difficult class for me to teach because it's never real world scenarios. Everything is very like carefully manufactured and very carefully set up to where we're not going to run into like, how would we do this in the real world type questions, because the answer is always very complicated and I don't want to go into it. But to me, this is actually, we're starting to get into more real world programs here. Okay, so this is pretty cool. I think this is as far as I want to take this example. Maybe we'll save this, and next class we'll get into the idea of a shopping cart, so that each time somebody buys an item, they're actually putting it in their shopping cart, and at the end we can check out, something like that. Maybe that might actually get complicated. We'll see. At the very least, what I want to do is next class do the object-oriented version of inventory. To me, if I were to write this program, I like this version. I like using dictionaries for stuff that's data. But we can actually rewrite the same program using inheritance. So just kind of describe quickly how you think you could rewrite inventory using inheritance. So what Apple and soda have a lot of things in common, correct? So do you think we could make a parent class just called food? And then food has a price and quantity. And then really, the only thing with apple and soda are just going to be the specific things to apple and soda. Maybe,
Food would have a list, right?
what's that?
Food would have a list. And that list would be a dictionary of apple, banana.
Yeah, exactly. There's a couple different ways we could. I'm going to have to think about this. The simplest way to implement it. That's why I'm always a little bit apprehensive. I really like dictionaries because it makes lookups very, very simple. And so now we've made our lookups a little bit more complicated once we get into class-based. But anyway, we'll worry about that Monday. Okay. So I think that's all I want to get into today. Any questions about this? Okay, so Monday I'll post the assignment. Just to let you know, this is kind of like we're in peak complication of this class. I know some of you, this is probably like, whoa, this is getting really complicated. But this is about as complicated as we're going to get for this class. And then throughout the rest of the semester, it's just going to be like reinforcement, doing more examples like this, maybe start using third-party libraries where we can start to do cool things. But this is about as complicated as I think we might want to get. I may even break it up into 2 assignments, a dictionary version and then a class-based version. Let me think about it. But anyway, for right now, just enjoy your weekend. Don't worry about it, okay? So if there's no questions from anybody, email me if you have anything. Otherwise, I'll see everybody on Monday.